Today we'll start our class on lyophilization of pharmaceuticals. Lyophilization is also called as freeze drying, and it is very important process and a manufacturing technique for pharmaceuticals that are sensitive to heat for degradation and also for peptides and protein-based formulations. We'll discuss about the introduction, theoretical basis of lyophilization, and practical consideration, formulation of lyophilized products, and the instrumentation that is used in lyophilization. Let us first start with the introduction to lyophilization. Lyophilization is defined as a stabilizing process in which the formulation is first frozen, that is separation of solvents and solutes, and then the concentration of the solvent, namely water, is reduced first by sublimation, that is the process of primary drying, and then by desorption during secondary drying to levels that will no longer support biological growth or chemical reactions. Stabilization after lyophilization is achieved by reducing the solvent component or components to level that slows down the degradation kinetics, which no longer support chemical reactions or biological growth. In the majority of the cases, this solvent is water, which is removed during the process of lyophilization. The history of lyophilization dates back to 1903 when rabies virus was lyophilized. Thereafter, in 1939, blood serum was lyophilized for the first time. Post World War II, use of lyophilization increased in food and pharmaceutical industry. The equipment that was used at that time was called as sublimator, because freezing was carried out at a different place, followed by sublimation of water. Now it is also used for non-biological products, non-living bioproducts like enzymes, hormones, blood products, etc., living organisms, herbal extracts, and food products. In the case of pharmaceuticals, lyophilization is applied in the following situations: products that are unstable in aqueous environment and for thermolabile products. It is also commonly used for sterilization of products that are finally to be presented at dry powders, especially dry powders for parenterals or dry powder for injection, and to achieve special functionality like mouth dissolving tablets, as is the case on Zydis technology, which was discussed in a separate lecture. The limitation of lyophilization is that it is an energy intensive and time consuming process and increases the cost of the product. Specific applications of freeze drying in pharmaceuticals include the generation of lyophilized sterile APIs in the bulk containers. The steps involved in generation or production of lyophilized sterile API include taking first the non-sterile API, dissolving it in water to get a solution of the API in water for injection, followed by sterilizing it by passing through 0.22 micron filter to obtain a sterile API solution, which is then freeze dried in a pre-sterilized tray and a pre-sterilized chamber of the lyophilizer to get the sterile API dry powder, and this can be then filled into the unit dosage forms by aseptic filling in pre-sterilized vials and plugs. This is a photograph of the bulk API container, which contains sterile cefotaxime API, and this can be then filled into individual vials to get the dry powder injections of cefotaxime sodium. The second application is lyophilized powder for injection, where the lyophilization is carried out in the primary container itself. In the previous case, we had lyophilized bulk of the API, which was then filled into individual containers. However, in this case, the lyophilization has been carried out in the primary container itself. So the steps involved in this case are non-sterile API bulk is taken and it is dissolved in water to get the solution of the API, which is a non-sterile API solution. Filter it through 0.22 micron to get a sterile solution, and which is filled into pre-sterilized vials and with pre-sterilized plugs, and that undergoes freeze drying to get the final unit dosage form. And the final product will look something like this, where the lyophilization has been carried out in the vial itself. Another special application of lyophilization is in the case of Zydis technology, which is used for the manufacturing of mouth dissolving tablet that are very rapidly disintegrating in the mouth. In this case, the steps involved are first mixing the ingredients that go into the tablet, followed by blister forming and filling of this suspension or solution into the blisters, which are then flash frozen, followed by freeze drying, followed by blister lidding to get the final product. Examples of products generated using Zydis technology include Claritin Ready Tabs, which is the mouth dissolving tablets for the Loratadine, and olanzapine orally disintegrating tablets that are sold under the trade name of Zyprexa Zydis. A special kind of packaging is used for these products that is called as peel off blister pack, and it looks like that. There are certain notches available for peeling off of the upper layer of the blister pack in this manner. So this is the peeling off of the upper layer of the blister. This is necessary because the tablet that is formed inside the blister are very soft, as they had not undergone any compaction process. They have been simply formed by the freeze drying and by formation of the leftover solid sediments. These are some marketed products made from lyophilization. So you can see they are available in glass vials, and the product is easily identifiable because it will be present as a cake form inside the vial, and this cake volume is equivalent to the initial volume of liquid that was filled in the vial before lyophilization. So during the lyophilization, this solvent is removed and it acquires the shape of a cake, which is similar to the shape of the initial volume that was filled in the vials. We now go to the theoretical basis of lyophilization. The lyophilization is carried out on the concept of triple point of water, and this is the phase diagram of water. Phase diagram means at a particular temperature and pressure, what is the phase of the water that exists. So there is a unique triple point where all the three phases coexist. And in this diagram, red color zone is for the solid ice, blue colored zone is for the liquid water, and green color zone is the vapor state of water. So triple point has a value of 0.0075 degrees Celsius and a pressure of 610 Newton per meter square, which is equal to 4.58 torrs. So these are the phase boundary. And if we understand this picture in more detail, O is the triple point where all the three phases, that is solid, liquid, and vapor coexist. OA represents the solid liquid interface. This is the OA line, and this is the solid and the liquid interface. OB represents the liquid vapor interface. So this is the OB curve, and OC represents the solid vapor interface. So this is OC. So boiling point of water decreases with a reduction in pressure, as is evident in the curve BO. So as the pressure is decreasing, the boiling point is also decreasing. There is a slight increase in the melting point of ice with the decrease in pressure, which is shown by the line AO. So you can see as the pressure is decreasing, the curve is moving towards the right side, which means there is a slight increase in the melting point. And the vapor pressure exerted by ice decreases as the temperature is decreased, which is shown by CO. So XD represents, so this line XD represents conversion of solid to vapor through the liquid phase, which means if we have solid ice, it will first convert to liquid water and then it will convert to vapor phase. Whereas YE line represents conversion of solid directly to vapor. So from here, the solid ice is directly converting into the vapors of water. So this is a phenomena of sublimation, and in lyophilization we exploit this conversion of solid ice directly to the vapor phase to achieve drying of the product by sublimation. So this is the set of conditions that we would like to use in case of lyophilization, so that solid ice can be directly converted to the vapors of water. So we will show this with an animation. This is the point which we will note down. So you decrease the temperature and pressure to condition so as to reach to this YE line, and then the drying is carried out to directly remove the solid ice into the vapor phase of water. So this is the theoretical basis of lyophilization, wherein we first freeze the water in the sample, and then the solid ice is directly converted into the vapor phase to achieve drying of the product. The steps involved in lyophilization include freezing step, primary drying step, and secondary drying step. We will first look at freezing step, that is done right in the beginning of the lyophilization process. Freezing step is important because the removal of solvent is accomplished first by freezing the formulation, which helps in separating the solute from the solvents and immobilizing any solute in the interstitial region between the solvent crystals. So this is the solution of a solute, where we can see that S represents the solvent molecules and A represents the solute molecules. When we initially freeze, a phenomena takes place that is called as freeze concentrations. In the freeze concentration, some of the solvent is removed from the solution by formation of the ice, and the remaining solute hence interacts with a lesser quantity of solvent to make concentrated solution, where the X% W by V, which was initially the concentration, is now present in a much higher concentration than X%. So if it was water, so these SS circles represent formation of ice. So because of formation of ice, some of the water which was earlier participating in the solubilization process will not participate in the solubilization process now, and the concentration of solute in the remaining solution will increase. And this increases up to a point which is called as the maximal freeze concentration, after which there will be phase separation taking place. So here more ice has been formed, and the concentration of the solute in the left out solution has increased to a maximum value. So beyond this, if we go, there will be a phase separation, that is solute will separate out from the solvent. So this is a transferred section of the frozen sample in a vial. So these white color zones indicate the ice crystals, while the interstitial space, which is shown in the sky blue color, has the solute plus unfrozen water. In the above diagram, this is the interstitial space where we have the solute and unfrozen water, while this represents the ice where only the solvent which has been frozen in the form of ice is present. After the maximal freeze concentration has been achieved, there are two events that are possible in the sample. One is that the phase separation takes place where the solute comes out in the crystalline form. Solute would be the, say, API present in the solution. In that case, we will observe a eutectic temperature, and the solute and the ice phase will separate out. The other possibility is that after maximal freeze concentration, the solute comes out in the form of a amorphous product. So this is a non-crystallizing separation of the solute from the solution. In this case, a glass transition temperature, which is denoted by Tg prime. So there is a comma which is there on top of Tg, and this is called as Tg prime. This also leads to the separation of the solute and the ice phase. We must note that supercooling takes place before nucleation because of the lag needed for nucleation, and even pure water does not freeze at 0 degree Celsius. So while we do the freezing of water, it will never take place at 0 degree Celsius. It will be some value which is lower than 0 degree Celsius, which means it will be a temperature value on the minus side. We'll here take an example of a crystallizing solute, which is sodium chloride. If we start with 0.9% solution of sodium chloride, it contains 0.9% sodium chlorides and 99.1% water. And at ambient temperature, only one phase, that is sodium chloride solution, exists. When we cool it, ice forms and water gets removed from the solution, thus increasing the concentration of the sodium chloride in remaining solution. At minus 20 degree, we will have ice crystals and a sodium chloride concentration of about 23%. and at minus 21.1, the concentration of solution reaches 23%, which is the maximal freeze concentration. And if we cool further, crystals of sodium chloride dihydrate are formed. So minus 21.1 is the eutectic temperature of sodium chloride, because after that or below that temperature, a phase separation of sodium chloride takes place from the solution of sodium chloride. Examples of materials that show eutectic melting temperature and phase separation in the crystalline form includes dibasic sodium phosphate, mannitol, sodium chloride, sodium iodide, magnesium chloride, and calcium chloride. And the respective eutectic temperatures of these solutes are given on the right hand side column. In contrast to crystallizing solutes, there are some solutes that will come out in the non-crystalline form or the amorphous form. And a common example of that is sucrose. If we take 5% sucrose solution, it will have 5% sucrose and 95% water. And at ambient temperature, only one phase, that is sucrose solution, exists. Ice forms and water gets removed from the solution when we cool it, increasing the concentration of sucrose and thereby increasing its viscosity. At minus 32 degrees Celsius, viscosity of the solution approaches 10 to the power 14 pascals second, and we will have ice crystals and a glassy mixture of sucrose and water, where about 80% of sucrose will be present. Cooling it lower than that does not alter the concentration, as ice crystallization is inhibited. So minus 32 degrees Celsius is the Tg prime of sucrose. These are some of the examples of solutes that come out in the form of amorphous form: dextran, gelatin, ficol, PVP, trehalose, lactose, sucrose, glucose, and fructose. And these are the respective glass transition temperatures of these solutes. You can note down that all of them are on the minus side, which is below the freezing point of the water. Another important step that can be included in the overall freezing phenomena is that of annealing. Sometimes the solutes come out in the form of an amorphous or a glassy mixture upon freezing, as was the case in the sucrose, but they may be crystallized with some subsequent heating. In such cases, an additional annealing step is included in the lyophilization cycle to promote solute crystallization. Annealing is simply heating the frozen system after the initial freezing process above the Tg prime of the initially formed glassy mixtures, but it is below the T eutectic of the system. So although we say that we are heating the sample, but this heating does not mean that we will be going on very high temperatures. This heating is a relative term, and it simply means that we will be heating it above the Tg prime of the sample. And this annealing temperature would also be on the minus side, but it will be higher than the Tg prime, but lower than the T eutectic of the system. The reason for this is to control the kinetics of crystallization. And a very good example of a system that can be annealed to convert the amorphous sample to crystalline would be mannitol, which means initially when we do freezing of mannitol solution, mannitol comes out in the amorphous form, but after annealing, the amorphous mannitol is converted into crystalline form. This is the pictorial depiction of the annealing step. So API, when we freeze it, comes out in the glassy form, and after annealing, it may show crystallization. And the examples of some solutes that show crystallization after annealing include gemcitabine hydrochloride and cefazolin sodium. While even after annealing, some solutes do not show any crystallization, and those examples include rabeprazole sodium and ertapenem sodium. So this is the end of our discussion related to the freezing step. Thereafter, we will be discussing about the primary drying step and its significance in the overall lyophilization process.